Alright, well, let's get started. If you're new to video lessons and online learning, then there's a few advantages you can use when you are watching a video of a lesson, and that's the pause button. It's really important. So if something's going a little too quickly, there's too much text, or the example needs you to try it first, then simply hit the pause button. If you don't understand it or you need to review it, the nice part is you can pause, rewind, listen to it again. So those are just some suggestions when you're doing online learning or video learning that really make it more effective and a little easier to work with. So we're going to move into linear relations, the straight and narrow path. Some of you might get that joke, but we'll be looking at, hopefully by the end of today, we'll be able to recognize and describe a linear relationship in terms of its graph, its table of values, and maybe even its equation. And this will be an ongoing theme for the next few days. So relationships show up all around us. We know that if you were to have 5 people, there's a good chance that 5 people are going to have 10 feet among them. If you move that to 6 people, there would be 12 feet. Those are just connections we have. We know that the more hours we work, generally the more money we make. So there are connections all around us, and we're going to investigate some of those relationships. Specifically, we're going to look at ones that we're going to call linear. So just a quick reminder from earlier, we had our horizontal axes and vertical axes arranged on a Cartesian coordinate system. I'm going to see if I can scroll that up a little bit. So we had this XY setup. I'll try and move that up a little bit so you can see it. There it goes. Whoop, a little too far. So the independent variable, that's going to be another term that's going to come up a lot in the next little while, is going to be our x-axis. Our vertical axis is going to be the our vertical axis is the y-axis, and that's our dependent variable, and those words will make more sense in the near future. They're both just number lines with positive and negative sides. So you'll notice here on this graph that I have a positive side on the right. Let's see if we can get my pen to work properly here. Come on, pen. There we are. So there's our positive axis. There's our negative side. So the number lines here, we would have 1, 2, 3, 4, etc. Going up in the positive y direction, we would have 1, 2, 3. And those numbers happen to fall right upon the lines. They're not the squares or the little lines that separate. And so that is our coordinate system. We highlight everything as an XY coordinate. So we put our left to rights first and our up and downs second. So the 0, 0 is right in the middle. That's the origin right here. And that's at the location 0, 0. So we kind of measure everything from there. So if we have the point 5, 6, I'll get rid of all that other stuff. So the point 5, 6, you can see if we count over 1, 2, 3, 4, 5, and then I go up 6, 1, 2, 3, 4, 5, 6. If I can get the dot to show up there, that would be the location of 5, 6. If I have this B location here of -4, -9, I would go back 1, 2, 3, 4. That's to the left, and then down 1, 2, 3, 4, 5, 6, 7, 8, 9. Hopefully that draws that a little bit bigger there. And that would be our location of B, -4, -9. Okay, so when we investigate patterns in numbers, we sometimes find there's a predictable or consistent relationship. And sometimes it's really easy to see, sometimes it's not. What we will use in the future are pictures, which we'll also call graphs. And we can see the relationships in different ways. So if I looked at these 3 relationships here, and you could pause it if you like. So now would be a good time to pause and see if you can come up with the next 5 terms. Okay, so the next 5 terms, if you've had a chance to try it, 2, 4, 6, 8. Some of you might start to see we can go 10, 12, 14, 16, 18, and we can see that these numbers, or this relationship, is going up by 2s. If we look at the next relationship, we might notice that, hey, 1, 3, 5, 7, those are also going up by 2s, but now they're the odd numbers versus the even numbers. And we could put the next 5 entries in, and it would look something like that. Okay, now the last one's a little different. It isn't quite so easy to see what the relationship is. But if you take a good look at your multiplication table, the diagonal line that runs right through your multiplication table, you'll notice these are all perfect squares. So the first value here is 1 squared. The next value is 2 squared, 3 squared, 4 squared. So the next group of 5 would be 5 squared, or 25. 6 squared, 36. 7 squared, 8 squared, and then of course 9 squared. And those would be the next 5 entries in that relationship. So if I asked you for any two numbers that have a difference of 3, so quick reminder, difference is subtract. So I'm looking for any two numbers that have a difference of 3. So if I took 6 and 3, if we subtracted those two numbers, they would be 3 apart. 12 and 9, those would be 3 apart. 15 and 12, those are all have a difference of 3. I could even be a little bit wild and crazy and do 103 and 100. Those are again 3 apart. So we're going to take that information, that idea that this relationship between these numbers has a difference of 3, and we're going to organize it a little bit differently. We're going to organize it into a table. So I'm going to do the exact same thinking, except I'm going to call my two numbers x and y. So I'm going to make a little statement like this. Y minus x, so that's the difference between two numbers, has to equal 3. And then if I go through the same process I did on the previous slide, I can come up with a whole bunch of numbers, but I'm going to look for a certain group. Okay, so I just picked using x values from 0 to 4, and then I figured out what the y values are that go with that. So if you notice, if I looked at 3 minus 0, that's a 3. 4 minus 1, that's a 3. And I can carry on and do all the rest. The last one would be 7 minus 4, that's a 3. So those two numbers, the relationship between y and x, they have a difference of 3. Now we have this term up here called first difference, so we're going to take a quick peek at that, and I'll define it in the next slide or two. First difference is how are these numbers changing? So if you look from 3 to 4, that is going up by 1. If you go from 4 to 5, that is going up by 1. And from 6 to 7, going up by 1, and 7 to 8, going up by 1 as well. If you checked on this side, you would also notice that all of these x values are going up by 1. And those are just what we call first differences. They're going to have some meaning to us in the very near future. If I was to plot this relationship, so if I take all of this table here, and if when I have 0, 3 in the table, it's a coordinate that looks like this, 0, 3. So I would come over to my graph, I would move, there's my x and my y axes, I would move 0 on the x, so I don't move at all, and then I would move 3 up and I would put a dot. My next value would be 1, 4, so that's a 4, so I would move 1 to the right and then 4 up and I would put a dot. The next one is 2, 5, so I would move 2 to the right and then 2, 4, 5 up. And you can probably start to see a trend happening here now. And that's the advantage of making graphs, is that it makes it really easy to spot the way relationships are connected. So in this one you could start to see that, hey, if I connected all those dots, they look awfully straight, almost like a line. Oh, wait, we're studying linear relationships. Whoa, there's our first linear relationship. So this is a place where you may want to pause and jot down the definition. The first difference is the difference between two consecutive y values in a table, which the difference between the x values is constant. So if you look back at the previous table, we had changes of 1 in the x column and changes of 1 in the y column, and those were our first differences. If the first difference is constant, then the relationship is linear. So let's just pop back here for a minute. Notice how all of these numbers right here were constant. So when those are constant, then what that means is we get a linear relationship. Why are you doing that? Thank you. All right, so let's try this again. Okay, so if we investigate this one here, we've got 4 figures with increasing number of sticks in each picture. So I want to try and draw the next 3 shapes. So what I might notice is, here's figure 4. I could start with figure 4, and you can see that each one is just adding, oh, get the marker going here. I'm adding 2 more sticks. So that would be figure 5 here. And then if I want to grab it one more time, this is figure 4, but now I have to add 2 sticks twice. So there's that one. And then I could do the third diagram, but I'm going to run out of space. So now what I want to do is just count up the number of sticks. So in this one I have 5 sticks, 7 sticks, 9 sticks, 11 sticks, 13, 15. And hopefully you can see that we could keep following this pattern by drawing out the shapes, but it starts to get a little bit tedious to draw that picture all the time. So what we can use, and this is where some efficiencies start to show up, is we can use a table of values and we can record all that information. So there's my first 4. We've already figured out 2 of the next ones, so if I could figure out, this would be 13, 15, and 17. So if we look up here, we had 13 and 15 for those 2 shapes, and now I've filled in the rest of the table. I could also plot this information. I've got a graph set up here. I can look at the first differences on this graph. I can say, how are these changing? These are all changing by 1. So that's kind of nice. These guys are all changing by positive 2, which is the 2 sticks I was adding every single time. And because this is constant, I would expect this picture to plot as a linear relationship. Okay, so even if I just plotted a couple of these really quickly, 1, 5, dot 2, 7, and then 3, 9, I can see those 3 are lining up really nicely, and I'm going to have a nice linear relationship that looks something like that. Okay, so now the next one, we want to find pairs of numbers that satisfy the following relationship. You can read this as 2 numbers that sum or add for 4. So I start with 0 a lot of the times because I find that's the easiest one. So when I look at this, if I put x equals 0 in here, if I have to add something to it to get to a 4, I know that answer has to be a 4. So the 2 numbers that I'm going to add together to get 4 in this case are 0 and 4. And then I'm going to repeat that, generating a whole bunch of numbers that will always, when I add them together, give me 4. So 1 plus 3 is 4, 2 plus 2 is 4, 3 plus 1 is 4, 4 plus 0 is 4. So all of those are possible answers. If I go the other direction, I can go into the negatives. That's completely allowed. I can see a 5 here. So a negative 1 plus a positive 5 should give me 4. And now you might start seeing a trend in the y column. So if I start at the bottom, 0, 1, 2, 3, 4, 5, you could probably predict the next number here is 6. And if you added 6 and negative 2 together, you would get the expected 4. And there we just filled in our table. If we do a quick check of our table of values, I'll only do the first couple here. These guys are changing by positive 1. Now this is a little different. These guys are changing by negative 1. Okay, so that's a little different. Now if I went to plot this information, I'm going to just take a couple of these coordinates here. I'm going to start with 0, 4, because that's a nice easy one to plot. There's that one. 1, 3, 2, 2, and 3, 1, and then lastly 4, 0. I can see I'm getting a linear relationship again, which is no surprise because my first differences were constant. There is something a little different though. This one is going down as we read from left to right, and we're going to talk about that in the days to come. Okay, so a relationship between 2 values that plots as a straight line is called a linear relationship. A linear relationship can be identified by its graph, which will be a straight line, so check, that one's not too bad to do. By its first differences, they will be a constant value, so that's not too bad to do. And by its equation. So we're going to talk more about this in the next day or two. We're going to talk about direct or partial variation and what first degree means. And this has to do with exponents. And all it is a recognition. Okay, so other important terms to know. We have something called a y-intercept. So a y-intercept is where our line or our graph crosses the y-axis. So in this location, it's right here. And you'll notice something about the y-axis, or sorry, the y-intercept. It has an x value of 0. So this y-intercept here is 0, 3. And this is a really big idea that carries through all the way to grade 12. And a y-intercept always has an x value of 0. Okay, now the other axes we can also deal with, it's called an x-intercept. Okay, so an x-intercept always has a y value of 0. So if I was to look at this guy right here, the location of that x-intercept would be -2, 0. And those are two big ideas that will show up throughout this course and all the way to the end of high school. So x-intercepts have a y value of 0, y-intercepts have an x value of 0. Mark that down somewhere. That's a really big idea. See if I can get to go to the next slide here. Okay, a linear relationship can be described in pictures, which we will now call graphs. A table of values, some of you might know it as an N chart, a T chart, sometimes use TOV, or an equation. And equations have different forms. I've given you one here of x plus y equals 6, and we'll see there's a bunch of different ways to write that. Or we can describe it in words. So when we're describing a linear relationship in words, the key words we really want to communicate to people are is whether it's going up as we read from left to right, and we call that increasing. If a linear relationship goes down as we read from left to right, it's called decreasing. And it's really important to understand that they're both from left to right, just like you would read a sentence. So increasing goes up from left to right, decreasing goes down from left to right. So is the following relationship linear? Now you can probably look at this table of values here. There's some pieces missing, but normally if you have 3 pieces of information in a row, you can start to make a little bit of a prediction of what's happening. So if I look at the first column, the x column, 1, 2, blank, 4. Okay, well we can probably guess that's a 3. So 1, 2, 3, 4, blank, 6. Well, we can go 5, 6, 7, 8. So that wasn't too bad to fill in. If I look at the y column, it's a little different. So -4, -2, 0, blank, 4. So there's only really one value that can split the difference between 0 and 4 evenly, and that's going to be a 2. Now, if I notice on the first differences side, I can see all of these are going up by +2. Well, if I keep working with that idea that these are all going up by +2, then the next value here is 6. The next value is 8, and then again that leaves me with 10, which is a number that was already filled in. Now because these are all constant, you should be able to tell me right away that this is a linear relationship, and if I plot a couple of values really quickly, there's a 1, -4, a 2, -2, a 3, 0, and a 4, 2. I can see those guys are going in the same direction. So if I wanted to describe this with a sentence, I may say something like an increase in x as x increases by 1, y increases by 2 in a linear fashion or in a linear relationship. The key words we want to get here are the increases. We're talking about whether it's going up or whether it's going down. That's a really important piece. Okay, this is one of those pages where you hit pause because I'm not going to read all of this to you, but we have 4 big words for today. Discrete and continuous data. Discrete data is data that you can't break up any smaller. So like the number of humans, you have 1 human or 2 human. You don't have parts of humans. Continuous data is stuff you can make smaller. So time, you could have half an hour, 3/4 of an hour, 23 minutes, 1.2 hours. So continuous is unbroken data. Your independent variable, and this is the formal definition of it, in a relation, the variable whose value you choose, usually placed in the left column. So for us so far today, that's been the x. So I can put a little x there. It's in the left column in a table of values and on the horizontal axis in a graph. The dependent variable in a relationship, the variable whose value you calculate, Okay, so it depends on the other value, usually placed in the right column, which we normally call y, and it's placed on the vertical axes. So I'm going to get you to pause for a minute. So there are 3 questions here. Describe the relationship between x and y values. Create a table of values using x values from -2 to 2, and then plot the following. So if you could just pause it here and try this. Okay, so hopefully you've had a chance to try it. So when we look at the first ones, or the first one here, we're going to do a describe. So y equals 3x. So the y value is 3 times the x value. Okay, not too bad. Part B, the y value is -2 times the x value plus 6 more. Okay, a little trickier. If we get our graph going and our table of values, let's see if we can scroll that up to make sure you can see it. So I have generated my table of values here, and just so we're clear how you generate that, you take the x value, you plug it in. So it would be y equals 3 times -2, y equals -6. That's the x value that goes, sorry, that's the y value that goes with that x value. And then as you move down the x column, or the x rows, you just keep putting in new x's, they generate new y values. So if you want to check your work there, see what the picture, or compare your pictures and your table of values, those are the solutions. And then lastly, a couple of questions to try on your own. So those are also listed on the web page, and I hope you got the important stuff from that, which is recognizing a linear relationship from its equation, its table of values, or its graph. Thank you.